Welcome back. In the last lecture, we have seen the basic introduction to vector and scalar magnetic potentials. Now we will solve one problem at least on either of these potentials, on both of these potentials. This is what we have discussed in our regular class, Ampere's law and its applications, and also in the SLT you might have gone through the different magnetic potentials. One is scalar, the other one is vector. So here I would like to recap them again. One is scalar magnetic potential, represented by the symbol U, and how it is obtained. The other one is vector magnetic potential, represented by A, and it is a vector, and it is given by that. So these two are the potentials which you do have in magnetic fields. Now, I hope that by the end of this lecture you will be able to compute magnetic potential for a given configuration. Now this is the problem which has been given for us. See, given a magnetic potential has been given for us. This is A minus R square by 4 UZ Weber per meter square, and they want to calculate the total magnetic flux crossing the surface. So this is the surface. Okay. For this surface, they want to calculate the total magnetic flux. You know, when A is being given, you can calculate phi using A dl. Or if you're not able to calculate this one, then better you go with B dot ds for the entire surface, because this is the surface directly given for you, so it will be easier to calculate in this way. So what is the surface? If you carefully see, the surface is phi is equal to pi by 2, which means it is constant in phi direction, whereas r, it is varying between 1 and 2, and z is varying between 0 and 5, which means that this is a cylindrical coordinate system. You do find r, phi and z, isn't it? So it is just like a cylindrical coordinate system where phi is fixed and one radius is varying between 1 and 2 and z is varying between 0 and 5. It is just like a, which means that this is r is equal to 1, I'll take, this is r is equal to 2, I'll take. So which means that at phi is equal to 90 degrees, it will be somewhere around in this direction. I'll take it as in this direction, which means that they want this particular region, and this area is spread over across in this fashion. So they want this region where phi is equal to 5 by 2, it is fixed, and r is varying from 1 to 2, and z is varying from 0 to 5. So in this region they will need magnetic potential. So that we will find out now. Okay. Now having said this, now first let us, we have already taken that we will calculate phi using integral B dot ds, right? So we need to first compute B. We have already seen in the previous SLT that B can be computed when A has been given for us. B is equal to del cross A, or we write it as B is equal to curl of A. Anything is fine. So del cross A. What is del operator? Del operator in cylindrical coordinate systems. As mentioned, this is cylindrical coordinate systems, right? In cylindrical coordinate systems, the del operator is given by in this fashion. We have seen this in unit number 1. This is your del operator, and this is my A which has been given for me. So I need to perform a vector product between this del operator and this A magnetic potential, vector magnetic potential. So determining the magnetic flux density by this cross product, right? So how do we do cross product? We do have UR, U5 and UZ, right? So the first one is dou by dou R. This is 1 by R dou by dou phi, and this is dou by dou Z. And these are in A, only UZ component is given by 0, 0, and this is minus R square by 4. So how to perform this one? See. So first of all, B is equal to, so I'll take it as UR bar cross multiplication, right? So this is 1 by R. If I differentiate it with respect to phi, there is nothing, there is no phi component here. So what I'll get 0 minus this one, I'll get 0, right? And this is minus U5. So here what I'm supposed to do, I'm supposed to do cross, right? Here also if I divide it, do it with the R, and this is minus is already there, and this is minus by 4 is there, this will become 2R, and here it will become 0. And the last term it is plus UZ. If I do it here in this fashion, you won't get anything, it will be 0. So the final answer is B bar is equal to, this will become 0, this will become 0. So here I will get 2R by 4, it is R by 2 U5, right? This is what I have written here. Now, if I do have B now, what I should do now? My next concept is determining the magnetic flux. How to determine the magnetic flux? It is, right, over this entire surface area. Now I have got B. What is B? B is R by 2, but is in this fashion. So what I should do now? Now I need to determine what is ds, right? Say I have already mentioned this is in cylindrical coordinate system, and if you carefully see, this is constant, right? So which means R and Z are varying. If R and Z are varying, we know in it will be having three different things, right? dr dz. This is constant, so these two are varying. dr dz I am taking. So now this is my expression for magnetic flux. This is B, this is P, and this is dx. This is the dot product. So this will become 1. So the remaining thing is phi is equal to integral of S R by 2 dr dz. And what is surface integral? R is varying and Z is varying. So I am going to write it in this fashion. Z is equal to 0 to 5 and R is equal to 1 to 2. Right? So first of all, let me complete this inner term here. So if I do integral with respect to R, what I will be getting here? I will be getting, this is 1 by 2 will be there. R will become R square by 2 from 1 to 2. But still dz is there. So what is this one? R square by 4, right? First if I substitute 2, what I'll get? So I'll continue here. So phi is equal to integral of 0 to 5. This is R square by 4, right? If I substitute 2, I'll get 4 by 4 minus 1 by 4. So what is this one? You can easily write it, right? This is 3 by 4, right? So this is 3 by 4 dz. Yeah, this is 5. Okay. Right. So 3 by 4, it is nothing but z from 0 to 5. So what I'll get? If I substitute 5 and 0, I'll get as 5 minus 0, it is 5. So I'll get 15 by 4, which is nothing but 3.75. This is what I have written here. So phi is equal to 3.75 meters. So this is the flux which we do it. Okay. So I hope that you have now understood how to solve these problems, and I am giving you a homework problem for you. See, a magnetic potential has been given for you, A, and you need to calculate B. You know, B is equal to del cross A, and I have given you for easier point of view in XYZ Cartesian system itself. So, and after that, you need to determine B at this particular point. Once you determine it, you need to find out flux also through the surface defined by C. This is Z is equal to 1, so it is extending in XY coordinate systems itself. Okay, so that's it for today. Complete the homework and come back to the class. Okay, thank you.